On day 34, students will begin Task 4, Thermal Energy Transfer. This task will ask students to investigate temperature changes and apply their findings to the final culminating project for the unit. However, this topic is often a very difficult one for students because of the many misunderstandings and misconceptions surrounding key vocabulary. Students learned much of this vocabulary back in Unit 1, but it will likely be necessary to review some of the important terms. Especially important, yet confusing, are the differences between temperature, thermal energy, and heat. It's helpful to remember that when we talk about temperature, thermal energy, and heat, we're really just talking about the movement of particles of matter. Thermal energy is just the total amount of kinetic energy in a system. Kinetic energy is the energy of movement. Therefore, when we talk about a substance's thermal energy, we're just talking about how much the particles in that substance are moving in total. If we could somehow measure the energy of each individual particle in the substance and then add that all together, that would be the total thermal energy of the substance. Temperature, on the other hand, is the average kinetic energy in a substance. We usually use a thermometer for this, but if you find the total thermal energy of a substance, then divide by the number of particles, that could tell you the average energy per particle, in other words, the temperature. These two diagrams provide a good way to visualize what it means for two substances to have different temperatures. Since they also have the same number of particles, in this case the one with the higher temperature also has more thermal energy. However, that's not always the case. This image is from day 36. Even if it wasn't labeled, it probably would not surprise you to learn that the human in the photo has a higher temperature than the ice-covered water he's climbing out of. But which has more thermal energy? It's actually the water. Remember, thermal energy is the total amount of kinetic energy in a system or substance. Although the particles in the person are moving faster on average than the particles in the water, in other words, they have a higher temperature, there are so many more particles in the water that their energy in total adds up to more than the much fewer particles in the person. Here's another way to visualize it. This simulation from PhET shows a quantity of water molecules in a container. Note the thermometer at the top. That shows us the average amount of energy in the container. But look closely at the molecules and you'll see that some of them clearly have much more kinetic energy than others. Some are moving faster or spinning more rapidly, while others drift around a bit more slowly. Adding heat to the sample unsurprisingly raises the temperature, but this increase in energy isn't uniform. Some particles are immediately affected. They start moving faster or spinning faster. The temperature doesn't tell us the energy of any particular particle, but rather the average across the entire sample. The distinction between temperature and thermal energy becomes important when we investigate the factors that affect temperature change, as students are doing this week. This diagram from day 13 illustrates this pretty well. It asks us to compare the speed with which ice will melt in cups 1 and 2 when water is added, especially when a different amount of water is added to each cup or when the water added to the cups is at a different temperature. Demonstration 3 is the most ambiguous. It's possible that the ice will melt equally quickly in both cups, because although cup 1 gets more water, cup 2 gets hotter water. It's not clear which cup actually has more thermal energy added to it. So that's temperature versus thermal energy. But then, what's heat? Although we often use heat and temperature interchangeably in everyday life, it's especially important during class to help students draw distinctions so that they can come to an accurate conception of both. Heat is the energy transferred between two objects due to the difference in temperature between the two objects. Heat travels from warmer things to colder things. It's easy to forget that heat travels from hot to cold. When we add ice to drinks, or air conditioners to our windows in the summer, we do it to cool down our water or our homes. But cold isn't a real thing, it's just the absence or reduction of heat. Cold things have less energy than warm things. The ice cools our drinks because some of the energy from the water is transferred to the ice, which melts it. Really, we're not cooling our drinks, we're warming our ice. But how does this work exactly? How is heat energy transferred from warmer things to colder things? This question from day 34 asks students to recall one form of heat transfer, conduction. Conduction is a form of heat transfer we already saw with the PhET simulation. Conduction occurs when particles with more energy bump into particles with less energy. When this happens, the slower particles speed up, just like pool balls crashing into each other. Since thermal energy is really just kinetic energy, this means that the particles are passing thermal energy from one to the other when they speed each other up. In this example, the part of the spoon that's in the mixture heats up from the water, but then the entire spoon heats up because heat is transferred along the particles of the spoon until the whole thing is hot to the touch. This same principle is why most pots and pans have insulated ladles, but why you have to be careful when using a solid cast iron pan that doesn't have such a handle. Not all materials conduct equally though. Here we have two squares, one made of metal on the right, and the one on the left is made of plastic. The temperature of the right square is about 74 degrees, 73.5, and on the left, the plastic square is about the same, 74 degrees. But let's take a look at what happens when an ice cube is placed on each one. Whoa, clearly that's a pretty big difference. How could this be? They started at the same temperature. Well, it's not always about the temperature that something's at, but how readily it conducts heat. Metal is a very good conductor, so it's taking all of its own heat energy and transferring it quickly to the ice cube, whereas the plastic does not transfer heat as easily. Here we see the final effects. The metal square now has a temperature of around 40 degrees Fahrenheit. The plastic cube has about 61 degrees. Big difference. This difference is just further proof that metal is a better conductor because it transferred more of its own thermal energy to the ice cube than the plastic did. This also explains why some materials feel hot or cold. For example, it feels nicer to step on a rug in the morning than a tiled bathroom floor, but really they're both at the same temperature. The rug just conducts heat more slowly than the tiles, just like the plastic conducts heat more slowly than the metal. Conduction isn't the only form of heat transfer though. Convection occurs when a fluid, such as water or air, moves thermal energy around. Here, water close to an ice cube quickly cools as it transfers its heat energy to the ice. This cooler water is now more dense, so it sinks rapidly to the bottom of the glass. This makes way for warmer water to take its place, which then repeats the process, creating a convection current. Because the water is moving, it transfers heat more quickly. This is also how a single radiator in the corner of a room can heat an entire room. Air near the radiator gains energy, which causes the air to move around the room, thus increasing the thermal energy and therefore the temperature in the room as a whole. Convection is a powerful form of heat transfer. Here we see the final third form of heat transfer, radiation. Radiation is the reason it feels warmer in direct sunlight than in the shade. Heat energy from the sun is transferred via electromagnetic waves. All objects radiate some heat in the form of infrared waves. If you've ever felt the warmth of a campfire, that's radiation as well. Temperature, thermal energy, and heat, conduction, convection, and radiation, although these terms are all closely related, they mean very different things. It's important that we choose our words carefully in order to better support student understanding.